Hi everyone, it's Jamie Batts for Bio 221. This is Chapter 5, and this is going to be the Part 4 video for this chapter, where we are continuing the discussion of metabolism. We ended with just briefly introducing lipid and protein metabolism in the last video, and so that's where we're going to pick up. And in the book, we're roughly, if you like to follow along with the text, we're roughly around page 930, and so what you'll see in this little section on lipid metabolism, basically I'll paraphrase it for you, the majority of fats that you're bringing into your body are converted into something called a triglyceride, right? When we are eating fats, we're eating triglycerides. That's the fat in the food. So those fats come in, and they're basically broken down into their components, which are a glycerol molecule and 3 fatty acids, hence triglyceride. So the glycerol is converted into pyruvic acid, and that pyruvic acid then enters the citric acid cycle. The free fatty acids are basically floating around in the blood. They could be floating around in the blood, or they could be absorbed into cells. In fact, cardiocytes like using fatty acids for their metabolism. They prefer fatty acids for their metabolism. And the reason is because they yield more energy than a typical glucose molecule. Now remember, the glucose molecule has 6 carbons, whereas the fatty acid can have upwards of 18 or 30 carbons in them. So the process of breaking down a fatty acid is called beta oxidation. And your book does not have a really good picture of it, unfortunately. But the idea is you have this really long carbon chain, again like 18 to 24 carbons, and the carbons are basically broken off into groups of 2. And those groups of 2 are converted into acetyl-CoA, which then enters the citric acid cycle and forms the NADH and the FADH2 and so on and so forth, just like with carbohydrate metabolism. So instead of having one 6-carbon molecule converted into 2 3-carbon molecules, you have this long chain, which is very compact, broken down into 2 little mini 2-carbon molecules, and those 2 mini 2-carbon molecules are converted into acetyl-CoA. So basically each fatty acid can yield, like, I forget the math, it's like 30-some ATP from just one fatty acid, and there's 3 fatty acids on a triglyceride. So you're talking about almost 100 ATP from one triglyceride molecule. That's why fats have so much energy in them. It's because of the increased carbon content in a lipid molecule. So just something to kind of think about there. So those fats can do different things as they're circulating around in the blood. Now, what I was just talking about with the metabolism, that of course happens inside the cells. And again, mostly we're talking cardiocytes. Cardiocytes like to use fatty acids as their main source of ATP. But after you just had a fatty meal, of course everything is routed over to the liver. Now remember that the fats are absorbed into the lacteals. So there's this whole kind of chain of events, and maybe I will get my little whiteboard out here and draw it out for you, because it's pretty complex. My little eraser sock. Pretty complex what happens to fats. So again, these fatty acids, make sure I move this around, dip this down a little bit. Okay, so fatty acids are basically absorbed or converted into something called a micelle, right? This micelle or mesyl, tomato, same thing, is basically a protein-coated fat. And that happens to emulsify and assist with absorption. So this micelle is absorbed into the intestinal cell, where it's converted into a chylomicron, or CM. It's basically a little fat droplet, and that chylomicron is absorbed into the lacteal. Remember, the lacteal is just this specialized lymphatic duct that's in those villi of the intestinal cells. So it's absorbed into the lacteal. And from there, it's going to go through the lymphatic system, through the thoracic duct. Remember lymphatic system anatomy. And the thoracic duct is dumping that fat back into the blood circulation. So it can happen in two ways. The thoracic duct can basically, the thoracic duct dumps the fat into the bloodstream, and in the blood it can interact with something called lipoprotein lipase, which is actually within the capillaries. And this is going to release, can you see this? Yeah. Something called FFAs. FFAs are free fatty acids. So instead of a triglyceride where you have 3 of them linked together, an FFA is just 1, free fatty acid. The other thing that could happen at the thoracic duct, again, we're talking about chylomicrons here. First, they can be converted by lipoprotein lipase, or these chylomicrons can be absorbed in the liver. Absorbed. Sorry, brain doesn't work. Absorbed in liver and converted to an LDL. So these FFAs are going to be basically absorbed by skeletal muscles. And you say, well, why would a skeletal muscle want a free fatty acid? And it's all about energy, right? Or they could be absorbed by the adipocytes, again, just for storage. If you have so many free fatty acids floating around, those adipocytes are just going to start sucking up those FFAs and depositing them for storage. The LDLs can go to the peripheral cells, and where the cells basically will use the cholesterol. Cells will use that cholesterol, right? Remember, cells use cholesterol in their cell membrane. And the unused cholesterol will basically leave the cell. Hopefully you can see this. So the cell uses the cholesterol, and the unused cholesterol leaves the cell, and it binds to, it basically binds together, rather, binds to form an HDL, which goes back to the liver. Now, if you know your cholesterol terms, you know that this guy is the good guy, and this guy is the bad guy. So basically, this HDL is a highly concentrated lipid form that's basically sucking up all the extra cholesterol that the cells don't use. Which is why when you go to get your cholesterol checked, they want to see, well, they want to see both of these numbers relatively low, but they want to see this number higher than this number. Because this number is basically saying, well, if you have so much LDLs floating around, that means you have enough cholesterol in your cells, and you have so much cholesterol in your cells that your HDLs can't even keep up with it. And so that's just kind of the pathway of lipid metabolism and lipid absorption. So again, those lipoproteins can have several different functions. Now let's talk about protein metabolism. I'm going to scoot back here so you don't just see the side of my face, right? Let's talk about protein metabolism. Proteins, when they're digested and broken down, remember, they're broken down into forming amino acids. And I briefly started talking about this in the last video. But there's two processes that will occur. One is called transamination, and one is called deamination. Transamination is basically where the amine group of one amino acid is replaced on another amino acid. So they're basically swapping amine groups. And one of the byproducts is something called keto acid. And what I'm describing for you here is what's on the diagram on page 934. Sorry, I dropped my pen. So transamination creates keto acid. And you say, well, okay, what the heck's keto acid? Doesn't really matter. What does matter is the fact that it is an acid, right? And what do acids do? Acids release hydrogen ions and lower the pH of the blood. And so what does that do? It's going to affect everything in your body. It's affecting your blood pH. So if you have a buildup of keto acids in your blood pH could drop if your kidneys aren't functioning enough, if you're not drinking enough water, if you have some sort of kidney failure. And that could be a very, very harmful condition. It could lead to respiratory issues. It could lead to more kidney issues. It could lead to whole system shutdown. All from protein metabolism, breaking down of proteins. The other thing that happens, or could happen, and again, it depends on which amino acid we're looking at. All amino acids, there's 20 different amino acids, and they're all broken down slightly differently. So some of them will be broken down using transamination, and some of them will be broken down using a process of deamination. Deamination produces ammonia, something else you don't want floating around your body. Ammonia is toxic, and the ammonia will float around and basically go to the liver, and the liver is where that ammonia will be converted into urea, and urea is what is secreted in the urine. That's what gives our urine that nice smell, the yellow color, all of that stuff. It's from the urea, from protein metabolism. So in the kind of big scheme of things, your body loves to use carbohydrates for breakdown, for energy. Super easy, super quick, very efficient. The more simple the carbohydrate, the easier it is for your body to break down and metabolize for ATP. Something like a lipid, your body doesn't mind doing lipids. It's a little bit more work because it's such a big molecule, but it's a big bang for your buck. Remember that beta oxidation is going to give your cells way more ATP than a couple of glucose molecules. Your body does not like to use proteins. Proteins are the last resort because of the waste products, the keto acid and the urea that are given off by the byproducts of protein metabolism. And again, each of these amino acids is going to enter the metabolic process at a different phase. Some of them will go to turn into, be converted into acetyl-CoA. Some of them will be converted into pyruvate. Some of them will be converted into citric acid. They all kind of enter that major chain at one point or another, depending on their overall structure. So, what you see on that was basically all of metabolism. Now, the next couple of topics in this chapter, and there's really just a few left, all have to deal with bringing nutrients into your body. So, if we think about what we do on a daily basis in terms of our nutrition, you go through times of eating, where you're physically putting the food into your body, and then the phase right after that where your body is then digesting and absorbing all of that food. And then you go through times of not eating, right? The couple of hours after you've ate, but before you eat again, right? Maybe like sleeping, for example. So those two phases are called the post-absorptive state, or I just want to make sure I'm calling it the right thing, the absorptive state. So you have the post-absorptive state and the absorptive state. In the absorptive state, you have several things that are going on. First of all, absorptive state means absorption is occurring. So this is that hour or so right after you eat, right? Right after you eat, you're in the absorptive state. Your blood glucose levels are going to rise. What does that mean? Glycolysis is going on and aerobic respiration is occurring. Lots of ATP is being made and stored for later. Your blood lipid levels are going to rise. So what does that mean? Basically, insulin is going to be used, and all of your fatty acids can be converted into glycerol, all of your fatty acids and glycerol can be converted and converted into glycogen for storage. Or, again, they're used to float around and break down into their FFAs or LDLs. As your amino acid levels rise, well, basically, those amino acids are then going to be broken down and reassembled into proteins for your body, assuming that you have the carbohydrates, that you have the lipids there in order to provide your body with energy. If you're on a low-carb diet, well, then you don't have those carbs there, so your body's going to start breaking down the proteins. It's going to create a hazardous situation inside your body. Remember, ammonia is being created, keto acids being created, both things your body doesn't like. So just something to think about as you may be trying different diet fads or whatever. During the post-absorptive state, so all of that absorption has occurred, the blood sugar's risen, the fatty acid levels in your blood have risen, and then they've declined as your cells have been sucking up all of those nutrients. Now your blood glucose levels are back down. You're not absorbing any more food, but you're not hungry, right? It's just, this is like the hour after you've ate. What are some things that happen? Well, glucocorticoids, which come from, the adrenal glands, glucocorticoids and growth hormone from the pituitary, those are going to stimulate pyruvate, and they're going to stimulate the whole glycolysis process, pyruvate into glucose, and the whole ATP metabolism process. You also have amino acids being converted into pyruvate and or released into the blood. And that's all because of the glucocorticoids and growth hormone. Right? So we're looking at kind of this cause and effect relationship. And I'm referring to my notes just to make sure that I'm telling you the right thing, because it gets kind of jumbly. So glucocorticoids and growth hormone are both responsible for creating pyruvate and getting the sugars out into the blood and then back into the cells where they need to be. You have glucagon and norepinephrine working together. That's basically stimulating glycogen to release glucose, to release it into the blood. So this is during that, again, that post-absorptive state. There's not a whole lot of blood sugar going around. You need something. All right, glucagon's being released. Let's call in the glycogen stores that are in the liver and skeletal muscles to be broken down, release that glucose into the blood. Glucagon and glucocorticoids are going to have an effect on your triglycerides. Basically, your fatty acids are going to be either converted into acetyl-CoA or free fatty acids to kind of float around. Your glycerol is going to be converted into pyruvate to start that whole process. So it's starting the process of lipid metabolism. Again, that's glucagon and the glucocorticoids. Epinephrine and growth hormone. All four of those guys are major mobilizers of fat reserves for metabolism in times when you don't have sugar floating around in your blood, when you haven't ate, when you're in a starvation mode, or when you're sleeping, right? And again, if you have too much acetyl-CoA being released, maybe from the breakdown of fatty acids, fatty acid metabolism through beta oxidation, that acetyl-CoA can be converted into that keto acid, which can create that ketoacidosis state, and that could be dangerous. So let's just make sure we're following along with everything in the book. You see there on page 936 the events of the post-absorptive and absorptive states, pretty much everything that I went through already, and just making sure I hit everything on the head. Pretty much I just summarized all of that. Final little section is about your metabolic rate. Your metabolic rate is the kind of timeliness of breaking down these molecules, and basically it's a measurement of how efficient your body is. Something called your basal metabolic rate, or your BMR, is how much energy it takes to sustain you. If you just sat at your desk all day, or not even sitting because that uses muscles, laying down all day, not doing anything, which still uses muscles because you're breathing, right? That's your diaphragm, you're blinking, your heart's beating, you're still using muscles even though you don't think you are. But all of those kind of life-sustaining things make up your BMR, basal metabolic rate. And that can easily be calculated, and it's not quite accurate. There's body types are different, and things like that. But on the whole, it's roughly mildly diagnostic, and that is by just taking a quick measurement of your height and weight. There's a little formula in that first paragraph there on page 938 under basal metabolic rate. There's also something called the thermic effect of food. And the thermic effect of food is basically the idea that energy is stored in the bonds of the food molecules we eat, right? We kind of talked about that already when we talked about ATP. Well, it's not a very efficient process because only about 10% of the energy that is within a chemical bond is then recaptured in a chemical bond. So in other words, energy is lost in the process. And that energy is lost in the form of heat. And guess what? That's good for us because we need body heat. We need to maintain a warm body temperature in order to maintain our enzymes and our normal body processes. So we need to bring in food so that we can break down that food and not only get energy from the food molecules in terms of ATP energy, but we also need the heat energy to keep us warm. And you may notice this mildly when you go to a restaurant and at first you get there and you're freezing because the air is blowing on you or whatever, but after you start eating the appetizer or after you're done dinner, you can take off your coat or you might be getting warm. And that's, again, the thermic effect of food. You get warm after you eat because the energy that's released from the chemical bonds when digestion is occurring is not 100%. It's very inefficient, actually, and 90% of that energy is lost in form of heat. So, let's see what else. Muscular activity actually accounts for a very small amount of the calories that you use per day. You know, when you are working out and you're trying to lose weight, more than likely, you know, you're maybe burning 400 calories after a really good, strong workout. So again, the bulk of your 2,000 calorie diet or 1,500 calorie diet is maintaining you and your basic life functions, your basal metabolic rate. The majority of the calories that you need are just to sustain you as a living being. And that all goes back to, again, the kind of body heat issue where we need to maintain our body heat to maintain homeostasis so that our cells can maintain life and our blood can circulate and all of those things. And heat is transferred through our body in three main ways. Conduction, which is the actual like touching of heat things, like when you're cold and you just kind of rub your hands together a little bit. That's all conduction. You're trying to get warmth from the other hand, right? Or you put those little hand warmers in your pockets, you know, when you're out in the snow. Radiation. Radiation is like standing in front of a fire and you feel that warm heat. You can feel it from the top of your head, right? If you huddle around each other on a cold day, you all say, let's get close together and use our body heat, right? You're actually feeling the radiant heat energy from the other bodies that you're close to. That's radiation. And the other way is through convection. Convection is basically heat lost from your head. A lot of the heat in your body is escaping through your head because hot air rises, so to speak, and that is the idea of convection. Hot air rises and cold air sinks. Hot air rises and cold air sinks. So that hot air is coming off of your head and sinking down to your feet and so on and so forth. So convection, conduction, and radiation are the three ways that heat is transferred. We lose heat also through evaporation. And that is through evaporative cooling, right? Sweating. Your body produces these sweat droplets, and as those sweat droplets evaporate off of your skin, that heat escapes with the water droplet. And that has to do with like complex things of thermodynamics, blah, blah, blah. I'm not going to bore you with that. But it's called evaporative cooling. It's the main way our body cools itself down. So that is, this lecture went a little longer than I usually like to stay, under 15 minutes, sorry. That is chapter 25. Just check the notes, make sure I was up on everything. There is a heat loss center and a heat gain center in your brain, and your book talks about it briefly, but basically it has to do with dilating and constricting blood vessels, and it's very much common sense. Your body always is working to maintain those stable internal conditions that we call homeostasis to keep our core warm, and it will sacrifice the extremities, because in the big scheme of things, if you're out in the winter and you're freezing, losing a pinky isn't quite as detrimental to your health as, you know, losing your brain or losing your heart. So all of this core stuff tends to stay warm, and the extremities can get sacrificed in those situations. Alright, that's enough for chapter 25. Please let me know what questions you have, and have a lovely day.